Morning. So we've got most of the team here.
Okay.
So we've got Alex, project manager, Matthew, programming and media, Ben, our electronics and robotics, and we have James, our ground station and outreach.
So who don't we have at the moment?
We don't have our parachute engineer and our structure engineer because they're doing some maths.
Yeah. And what are their names? Sorry, so I can just check them.
So it's James Tyso.
Yeah.
And Bradley Dowsett.
James Tyso, Bradley.
Edward.
Oh, and also Edward Kitteringham. He's our new person. He's working on the airbag system.
Okay.
Yeah.
Right, guys. So how are we feeling so far about the project?
Yeah, it's been good, thanks. Yeah, we've been learning quite a lot. Quite interesting how it's all turning out. Yeah.
Okay. Are you finding it quite challenging at the moment?
The electronics is quite challenging, yeah.
The electronics is quite challenging. Well, I've got with me on this side Will Addison. Hello.
Hi. Hello.
Hello.
So do you want to just explain a little bit about your experience?
Okay, sure. Hi guys, my name's Will. I'm an electronic engineer at Surrey Satellites. I spent 2 years in the imaging department on the cameras on the satellites basically, and now I've just spent a year working on the avionics and radiation monitor as well. So I've got electronics backgrounds. Unfortunately, where I missed out, Pete makes up, so we make a good team. So on the mission and deployment side of things. But I should be able to help out with all the electronic stuff and some of the software stuff too.
Yeah.
Okay, so basically what we want you to take away from that is please feel free to send us questions. And any question, there's no such thing as a silly or a stupid question. And feel free to either email myself or Will, and we should be able to help you with your electronics software questions that you may have at this moment in time.
Yeah. One question we have is we've got some sensors, and we've plugged them into our Arduino boards, and we get loads of data from them. But yet when we plug them into our CANSAT boards, they don't. But the board seems to be working because we've got data from it before, but now it doesn't seem to be doing anything.
What is your CANSAT board?
It's supplied by a company called T-. They're out in Holland.
I'm reading the spec on the sheet. The Arduino.
Can you, after this meeting, can you send the specification sheet, i.e. the data sheet about that board, to Will, and he'll be able to give you a good comment on it.
Okay, yeah, thanks. We'll do that.
Guys, I couldn't find that board in the spec. I just saw the Arduino. I thought you were going to fly the Arduino.
Oh, it's ESRO, the organisers, they supply all schools with a generic board supplied by T-. The reason is the boards are designed so they fit nicely inside a can.
Okay.
So the generic Arduino cans, because they're a bit elongated, they won't really fit inside properly. So they've designed specific boards that everyone can use.
Okay.
Yeah.
Okay, so send us the details on that board. The other thing that you may want to consider is talking to ESRO and either getting a spare board, a redundant board, just in case, or raise the issue because other CANSAT competitors may be also having a similar issue. So don't think that this may be an isolated problem. Ask for help if needed.
Okay, yeah, thanks.
So, Alex, I sent you I sent yourself and Gurmit an email. It bounced from Gurmit because it was quite large. It contained a few examples of some documents. Did you get that?
I don't think so. I haven't seen it yet.
Okay, it's about 11, 12 megabytes large. So,
I think our emails are maxed out to 10 megabytes, so we can't receive anything above that.
All right. Well, I'll send that again then.
Yeah.
So what I wanted to bring up, because we've only got 45 minutes, is a few things about the technical aspects, technical comments, and also just about the structure of the document, the draft document that you sent us. Okay. So what I've done is I've sent you three examples. One is a scientific paper. One is an example of a report, a project report, and another one is an example of a project proposal. So when you want to try and gain money from research councils, you have to put in a proposal to gain money. So I've put those three documents into an email last night, and I sent them off. They obviously haven't arrived, so I'll chop them down into smaller emails.
Yep.
And what I'd like yourself, Alex, if at all possible, is have a look at them. You don't need to read all the details and all the pages and stuff in there, but I'd like you to just get a feel for how in the academic and engineering worlds we actually structure and format documents. So just simple things like page numbers, contents pages, list of figures, appendices, and reference citations at the rear. All right?
Yeah, that's fine. I'll take a look.
Brilliant. Okay. Also, in the first few pages, just trying to find where. Okay, in the first few pages, you basically say that by the second report, i.e. this one, I presume, that you guys will have a design of the complete, preliminary design of the complete system. And what I've noticed is that you guys have all gone off and looked into your separate areas and reported back on ideas and so on. But it doesn't seem that as a group, from reading this report, that you guys have actually come together and figured out how you're going to put all of this technology and all of this into a single design.
Yeah, we actually had it planned for Wednesday when we were going to come and brainstorm with each other. That's pretty much the only 3 periods that we have with each other where we can really all be together as a whole group.
Right.
So we feel that if we are all separate, information might get twisted with each other.
Okay, so going back to the structure of the project, we've got, who again is the systems engineer? You've got Bradley.
Yeah, that's Bradley. At the moment, Bradley's doing combined cadet force.
Right.
So his role is he has to teach all the students how to become cadets. So I think at the moment he's overloaded. So I think we might have to ask someone else in the team to take that role.
Okay.
Yeah.
So yes, it would be nice to have everybody sit down around the table. But as you can probably find out yourselves, it's hard to find time for everybody to be in the same place at once. So it's usually the responsibility of the systems engineer and the structural engineer to work together to finalise the design. So it doesn't need everybody to be there to input. If you were to do it as we would in the in the actual space industry, it would be those two people, the systems engineer and the structural engineer, which would come together and design the actual satellite. What we do is the system preliminary. What we do is the systems engineer, the structural engineer, gives blocks of space. Okay, so we say that 2 centimeters by 4 centimeters by 5 centimeters blocks of space that can be used for the Arduino. That part of that area of the satellite, which is 10 centimeters by 2 centimeters by 1 centimeter, that block of volume that can be for the airbag deployment system, etc., etc. And then all of the other project people in the project team know exactly what volume they have to then build their system to. Okay, and then you divvy out the space. You then have the project engineers build their system within that volume, and then all of the bits and pieces come back together again into a final design. Obviously, there will be a bit of toing and froing, a bit of negotiation, because maybe a particular screw or some wires won't fit in the volume, and you have to make judgment calls and so on. But that's basically where we start from. And the same goes for power, and the same goes for mass. So we give each project engineer a volume constraint, a mass constraint, and a power constraint. Is that about right, Will?
Yeah, that sounds good. Because I noticed you guys wrote that you don't want to exceed the power budget, for example, on the battery. I was just wondering if you've done any calculations on that.
We've done a bit. We haven't done that much yet, but we've done 600 mAh, around about that.
You've got a 600 milliamp hour battery.
Yeah.
Okay, cool. So sorry, I've got suddenly gone very technical, but yeah, just to back up what Pete's saying, if everyone produces power, weight and size budgets, then that's what the system guy needs to control. Are you happy with that?
He's not there actually. He's well, yeah.
Okay.
Does that all make sense?
Yeah, so splitting up the CANSAT into different parts for each different engineer.
So you've got each engineer is responsible for a particular system, okay, and then you divvy out the volume, the mass, and the power appropriately. So some project engineers may need more mass but don't need as much power. Some engineers may need more power but actually don't need a lot of area, a lot of volume.
So that's why it's important for the system engineer to correlate that and to work out the budget.
Okay.
Because otherwise you'll just be making numbers up.
Is it, in normal projects, it's fine that someone changes their role midpoint, isn't it? Would you say? Or because I think... Because at the moment Bradley's a bit overwhelmed, so we're thinking maybe we have someone else take on his role.
Yeah, I mean, that's, as a project manager, Alex, that's your responsibility to ensure that the team is working together. And so if Bradley is overloaded, then you need to make a call and change your team members around.
Yeah.
But yeah, so you've got to get on top of that sooner rather than later.
Do you have someone in mind, Alex?
Probably our electronical engineer will take over for systems as well.
So Ben, is that Ben?
Yeah, Ben.
Oh, okay.
Okay.
Yeah.
Try and sound enthusiastic about it.
Right, there we go. It sounds like baptism by fire. Yeah. It sounds like you've been landed with it. Fair enough. It happens here all the time. Okay, so if people go away on maternity, paternity leave, or people are ill, or people get moved projects, then it happens here all the time, and people just have to deal with it and get on with the job.
Yes, Ben?
Yeah.
So we've talked to... I'll send those layouts of those examples of those papers, and basically what I want to get across to you guys from a project report point of view is that you've got to think about telling a story, all right, of the project, and not everything that you do. It may be very. Please don't take this the wrong way. It may be very interesting and important to you, but it might not be as important for the end reader to read. So you've put lots of information in the report about what you've done, where you've done, and as you've updated and done new things, you've just put that into the report. Now that's all very cool and very good. It shows that you've done lots and lots of work, but when you're an end reader, okay, you've got to be asking the question, do I need to read all of this information, especially if it's now not necessary? So, for instance, reading through the report, you've still got bits and pieces about the points-based system, which you've decided not to do anymore. So the question is, do you need to tell the person reading the report that amount of information? And the question is, you may turn around and go, actually, yes, I think we do need to do that, which is perfectly fine, but I just want you to think about that.
I think with the project, they want to see an evolution of design, so should they just put it in the appendix, or?
Absolutely, that's my next point, okay? Use your appendix and so on. So the main core of the report should be the minimum and so on. I remember being at university and writing a 10,000 word report, okay? My supervisor turned around to me and said, take it away and rewrite it in 750 words. Okay? And that was incredibly difficult because I'd done lots and lots of work, but I had to realise about what was important to actually get across in the project. So I'd like you to do the same thing, okay? If I may, and that is, for the next time that you write the report, I'd like you, in the main part of the report, that every section is limited to 250 words. Okay? So 250 words. So every section, my definition of every section is every time you have a new title. Okay? So if you want to write more words, then put in new titles.
Okay.
Anything else which you don't think is important to the story, but you still want to report on, put it in an appendix and put it at the back of the report.
Make sure you reference in the report the appendix as well. The appendix has got to have meaning. So don't just stick loads of stuff in there with no reference in the rest of the document.
Okay.
Okay?
Yep.
Okay. So, an example. Okay, the next thing I want to get across is that you guys are running out of time. You've got 3 months to get this built, tested, designed, built and tested, and test and test and test and test again. I cannot stress how important that final phase of testing is. What we usually do is it usually takes us about a year and a half to build a satellite, and then we'd be testing it for maybe about 6 months or so before we hand it over to the customer. So we do a lot of testing on our satellite, and you guys need to do the same on your CANSAT as well.
Okay.
So basically, what I'm trying to get across is that you've got to get a move on with this design. You've got to start building the thing. Okay.
Yeah.
Yeah. Agreed.
How far are you guys along, just out of interest?
We've started testing the components and started to assemble it outside of the can, but we haven't started putting it inside the can yet.
Okay. Yeah, that's fine. I mean, what we have here, Pete's very familiar with, is we call it soft stack and hard stack. Now, hard stack's when the satellites all put together, and soft stack's when the things spread out on the table. There's almost like a system diagram, but on the table. And that's really useful if you've got problems with it, because you're able to swap things out and get things get to the components easily. I mean, with the
do you understand what we're talking about there?
Yeah.
Okay, so just to be absolutely clear, think of like a computer, all right?
Mm-hmm.
Now, a finished product would be the computer in its case, all as a single desktop kind of computer. Well, that would be our equivalent of a hard stack. Okay, a soft stack would be all the individual components of that computer. So the hard drive, the power system, the motherboard, the graphics card, etc., all laid out flat on a table with wires and so on connecting up between the systems. That would allow us to run the computer as a computer, but would also allow us to probe with voltage probes and test measurements and so on different parts of the system. Does that make sense?
Yeah.
Okay. Okay, done that. Added on.
Guys, I'm just a quick question on the technical side. So when you've got the Arduino, I use Arduinos all the time. They're brilliant. And then with this new board that Esro have provided, is it the same programming language? Have you had to change anything?
Yeah, I think it's the same programming language, but the issues is you've got to program each pin. So I think there's an issue with you got to sign it as digital, analog, and output and input. So I think
with the Arduino you get 8 analog channels and 13 digital channels, but on this board you have to tell it which one it's going to be.
Yeah, some of them have been assigned as digital, but it's I think they've written a program that's compatible with Arduino programming, but with some of the ports you have to like preset yourself.
Okay.
So I think that's where the issues are happening.
Okay, cool. Just keeping an eye on the time. It's Ben on the electrical side, and who's the software guy?
Me, Matthew.
So if I'll get you guys on email, and then I can see what you've got so far.
Okay.
I was wondering if they would let you use an Arduino. Just my gut feel is designing it on one thing and then shipping it across to another.
It's
really tricky.
So what I did first was they got the Arduino boards first. They're testing on those because it's easier to use, and then now once they validated it on the Arduino board, and now they're trying to use the CANSAT board, and then the problem is not picking up data.
Okay.
Yeah.
I read in the report you were saying you're going to simulate an environment to test the Arduino with.
Yeah.
What are you using? Are you using physical sensors, or is there software that you're using for that?
Most of them are real sensors, so they're buying the sensors and then testing them, and then integrating them afterwards. So they've been doing.
That's always the best way to actually have physical hardware that you're testing.
Yeah.
Than using modelling. It's always good to actually have the actual things in place working.
Yeah.
Just looking at the requirements, I reread the requirements last night, and I just want to draw your attention to HAE 16. Okay, the CANSAT shall be able to withstand an acceleration of up to 2G for balloon launch or 20G for rocket launch.
Yeah.
Okay. That's a very interesting requirement.
It was set out by the organisers. It's the organisers' requirements.
Yeah, absolutely. I understand that. It's a very interesting requirement. I think you guys need to look at that in detail. I think you need to do some research and understand exactly what that's asking for you, because it's not as straightforward as you may think.
Okay.
Obviously, if you've got further questions, come back and we'll explain a bit more. But first of all, it's probably a good idea if you go and try and figure it out for yourself to begin with. Okay.
I just emailed you the CANSAT documents regarding the electronics.
Brilliant, thank you.
Yeah.
You sent that to Pete, have you?
Yeah, I've just done that now to you and both of you. Yeah.
All right, brilliant.
Okay. Thank you.
So just whizzing through the reports. There were some really good parts. I don't want to be too negative or critical. Some of the added bits that you did put in are really good. You've obviously thought about things, and you've also put a critical eye and thinking to sections. So, so I don't want to be too negative about it all.
Yeah, that's okay.
And I love some of your update reports. I love that you've tested things in a bell jar in a vacuum.
Oh, wow.
That's really good to see. Okay, so one of the things that I think you guys need to think about is firming up your some of the mission requirements. So at the moment, you're looking specifically at your soil experiment. You're looking at different terrain types of around what Earth would be like. Perhaps you may want to focus on a particular planet. Okay, so if it's Earth, by all means, carry on with the experiment. But what happens if you're thinking about trying to go for landing on Mars or landing on Titan? Okay? Will your requirements for the soil and the seed and the plant requirements be different in those cases? Just want you to think about it. You don't need to massively change things that you're doing, but I just want you to have a think about that.
Yeah, I'll get onto that.
Okay.
When I was looking at it, just going by exoplanets, so I thought, as Earth is, probably one of the best exoplanets in the galaxy, sort of thing. I was going off that. But I wasn't really thinking about Mars. But yeah, I'll look at other planets like Mars, Titan. Give me an idea for seeds.
The whole idea behind the CANSAT is terraforming. Okay, so you've got to think about which places in our solar system are we most likely to terraform first, or try and inhabit first. And those are probably either going to be a moon base, are going to be a colony on Mars, or Titan, because there's a lot of abundance of water and ice there. So you got to think about those three areas, and then you got to think about what kind of plants and seeds may survive in those particular environments, or maybe not even plants. What sort of organisms may survive in those environments?
Okay. Yeah.
Okay.
Yeah.
Right.
They're actually going tomorrow. Have you heard about the space design colony competition?
No.
Yeah. So it's called UK SDC, and some Alex, Matthew, and James, and some other students are going tomorrow. So they spend the whole day designing a space colony from scratch at Imperial University.
Yeah.
So hopefully they'll be learning some transferable skills from that tomorrow.
Absolutely brilliant.
Yeah.
Sounds fantastic.
So, and I think James, he's a bit sleepy at the moment because he had his project last night. So, with the Cs, what they're planning to do is get primary schools involved, because we get points for outreach.
Yeah, absolutely.
Yeah, so they wanted to get the primary schools, to do grow some seeds under different conditions.
Okay, the comment I've got on that, okay, is yet again, you've only got 3 months, of which 1 month is Christmas, and so you're going to expect a lot of disruption around Christmas time as people go on holidays and Santa Claus arrives, etc., etc. Don't tell me you don't believe in Santa Claus, because I do. So there we go. So also I noticed that in your experiment you're asking for 3 weeks. Okay, so you may want to think about that, because first of all you've got to approach schools, you've got to see if they're interested. Okay, that's not going to be a couple
my
of
little
days. That may
sister's
take
school
some
already
time.
said I could come
Once
to
they're interested, and you've then got to set this experiment. It then takes for 3 weeks, and then from that you've then got to make a decision. And then the question is, does this decision feed back into the design? And if it does, then that's 4, 5, 6 weeks that you're waiting for a decision before you decide what to put into the satellite. So you may want to think about that again. I'm not saying it's a bad idea. I think it's a good idea. Okay, but you may want to think about the particular details of it again. The other thing you may want to think about with outreach is that you guys haven't got a name for your satellite yet. You've got a name for the project group, but you haven't got a name for the satellite. And one of the fun parts of any satellite is making up names. So So we've got Novasat, we've got Disaster Monitoring Constellation, we've got Strand, or Stranded. So one of the nice things to potentially see is a name for the satellite next time in the report.
Okay.
I think we'll have a lot of fun naming a satellite.
Huh?
It sounds like it could be a lot of fun naming a satellite.
Exactly. Okay, so I want to talk about your airbag deployment system that you guys have started planning and designing. Who's in charge of that? Is that Ben?
That's Edwards, but he's sick today.
Is he here?
No, he was he had a high fever yesterday, so he went home.
Right, okay, fair enough. Okay, so I want to reiterate my comments from the last telephone conference, and that is that the more complex, and this goes to the robotic arm as well, the more complex the idea, the harder it is going to be on the structural engineer to accommodate and for the power system and so on. And something which is more likely to go wrong. So you very much focused on trying to replicate what NASA have done. You've got to remember that these probes, that they have these huge airbag deployment systems. These probes are the size of a mini, okay, or even a couple of large washing machines. Okay, these probes are quite big, and so they have the space to have these elaborate airbag deployment systems. This is something that you guys probably won't have in your CANSAT, and as you bring the design together, you will notice that there will be an extremely lack of space in there with everything that you want to do. So you may want to think about looking back at the requirements again, and looking back on different ways of doing things. And I'll just give you a few examples. The requirements ask you that the can will be dropped at a speed of 20 meters a second. Yeah.
Yeah, it's that's an ESRO requirement. It has to be 11 meters per second.
Yeah. Okay.
Yeah.
Okay.
So I think when I was at a teacher event, some people say that's a bit too fast, but they're saying it has to be 11 meters per second because it might be in the middle of a field, and if it stays in the air too long, it could drift too far. So they're saying that's why it's such a fast descent rate.
I think that may also be because the parachute may not open. If the parachute doesn't open, you're going to hit descent rates of that speed. Yeah. If the parachute does open, it's very much likely that you won't be going as fast down.
Yeah.
I've just got a question actually. If we got forces equal to mass times acceleration, the mass of your unit's very small.
Yeah.
So it might even be able to withstand the impact, just given its light mass.
Yeah. So it's only 370 grams, and so you guys need to do some drop tests on a can of 370 grams and see exactly what will happen at different heights, and then basically just do some simple maths and physics workings out to find what sort of force you would have on the can on impact. And then you may want to think about some passive kind of systems. So, for instance, packaging companies, when they've taken their big high resolution TV screens, they use high density foam. Okay, so all you're trying to do is take out the shock of it. In cars, they have crumple zones where part of the car is designed in a crash to actually crumple whilst protecting. Whilst there's a reinforced area which protects the actual passengers.
Yeah.
You may want to think about maybe having a crumple zone. You may want to think about high density foam. You may want to think about shock absorbed systems using springs inside. You may want to think about another idea that I had is if you had a syringe and you had some sort of compressible fluid inside that syringe, then if the syringe was attached to the CANSAT and it was the syringe point was the first to impact, so where you would usually press the syringe, you would use that as your leg type thing, and so when it then hits the ground, it could then compress and it could absorb the shock. You know, so you guys want to think about passive systems. So yet again, trying to move away from electronics and motors and gizmos and gadgets, and just go to some really kind of simple but effective passive shock absorbing techniques.
Yeah. Okay.
And as an example, I mean, you could get on with that straight away. So you could get like an egg. You know, you could put an egg in the can, and then you could design a shock absorbing system. And if the egg doesn't break, then hey presto, you know, on impact. If the egg doesn't break on impact, then hey presto, you've got a decent design.
Okay. Yeah, that's a good idea. Thanks.
All right.
So, yeah, things will fall to ground on Earth at 9.8 metres a second, or that's acceleration. So you could, if you double the weight, then that would produce the same amount of Newton force.
Yeah.
So if you've got something that's around 700 grams and you drop it from a height, then that's very representative of what you could be experiencing for the CANSAT.
Mm-hmm.
Okay. I like that you've thought about using a quadcopter to do your drop tests. That's very cool. Enjoyed reading that. Okay, so the same with the digger as well. All right, you've got a very complex design. Anything with joints, pivots, points, movements, and so on. You know, it's again with a robotic arm. You've got to ask yourself exactly why do you want the robotic arm on the system, and it's a very complex design, and I think you're underestimating the amount of space that will be eventually required for it. So yet again, you may want to have a think about that in more detail. I've got a note here about a lot of the satellite probes, which are, if you look at the Philae launcher, or the Philae satellite, which was just launched from Rosetta and landed, the main thing that they used to get soil samples was a drill, okay? And it was basically using the Archimedes screw principle, okay, with the drill. So they would drill into some rock, and using the Archimedes screw principle, material would travel up the central barrel of the drill. So you may want to have a look at that and think, is that something that we would want to do instead of having a robotic arm type system?
Yeah, that'd probably be something a lot easier to make and put in the can than a robotic arm.
Yeah, we have.
Again, these are all just suggestions. Doesn't mean that you have to agree with what we say. Okay, at the end of the day, it's your project, and you guys make the decisions. Okay.
Yeah, I've had some. I've already had problems with space because Edward's airbag. He wants a lot of space for his airbag, and I need quite a bit for my robotic arm as well.
Yeah, the other thing that I noted on the airbag deployment system, yet again, it was this idea that you have no control, unless you design the CANSAT properly, you have no control of which direction the CANSAT will be falling, okay? And in your airbag design specifically, if you have a lot of airbag at the bottom of the spacecraft, it will mean that the centre of gravity, the centre of mass, is more towards the middle of the can. So it means that when it's tumbling through the air, it will tumble in all directions. To ensure that your satellite is falling in one particular direction, you need to ensure that the centre of mass, the centre of gravity of that satellite is towards the lower end of the can. Of the CANSAT. That basically means ensuring that it is mass heavy towards the bottom. All right, that way there will be a tendency to pull the as it tumbles down to fall in an upright position. Do you understand what I'm trying to get at?
Yeah.
Yeah.
And how do you suppose that we test it to say that there's not too much weight on one side of the can than the other?
Drop it from get permission from your teacher and drop it from the second or third story, or drop it from the quadcopter, and just iterate design after design after design. That's why I'm talking about testing is really important. Okay. Also, if you're having troubles with the CAD programming and making 3D designs, then my advice to you, Alex, just ditch the idea of creating a 3D model and then just go straight into building and testing, because it's the testing, the reiteration of the design, the testing, the reiteration of the design. That's what will get you a decent final design. Okay?
All right. Yeah.
There's an expression one of my project managers uses, and it's we fly the satellite, we don't fly the paperwork. So just to reiterate what Pete was saying, it's really nice to have that 3D model, but that's not the end goal. That's not the satellite itself.
Yeah.
There was an idea of building the robotic arm 3 or 4 times bigger and then scaling it down. I would propose that's a bad idea. Okay, the reason is that you're not building something which is representative of what you're eventually going to use. Okay, it's very easy to create something big, but the difficulty is in the miniaturization. So you just need to get on and get over those issues. So if you're going to build something small, start small.
Yeah.
Yeah, right.
Your NAT chart and task list with your percentage complete, that was very, very good. I like that a lot. It gave me a very quick and clear indication of where you guys are in the project. So yeah, good effort on that, and it's well populated. My only point of note on that one is that you've apart from the project management part, you've only really reported on the things that you've done or you're going to do in the immediate future, and you haven't really put down tasks of what you may be doing in a month, 2 months, or 3 months time. It's important to have those goals and deadlines set a long time in the future. Do you understand?
Yep.
Okay. You said that you're talking with a company about the programming of the software.
Yeah, that's it's called CGI.
Okay.
We had
And then you have a talk with them in January.
Yeah, we try and get. I think they're busy at the moment, but we've also got ExoMoles involved, so I've sent them the report as well. There's 2 engineers that are going to have a look at their report, and then they're planning to do a teleconference with ExoMoles in January.
Okay.
And if that goes well, hopefully we'll take him out to Holland to go visit ESTEC.
All right.
Yeah.
That sounds amazing. Sounds like a really good opportunity which you should follow up on, because that'd be very exciting. My only comment is that January is yet again it's a month down the line, and so that's 4 weeks that you're losing.
Yeah, true.
4 weeks that you're losing on getting on with the software. So it's really good that they're going to do that for you, but you need to get on with that programming the software and getting over that.
Okay.
Okay, so that's mostly through the thing. Next time we have a project meeting or a teleconference.
Yeah.
Okay. What usually happens with teleconferences, here at SSTL and in the engineering industry is that the project manager will come up with an agenda, and then it's points on that agenda which are then discussed in detail.
Okay.
So it just gives a bit more focus to areas that you as a team would really like to hear about and discuss in detail.
Okay.
So the next time we have a project meeting,
Yep.
could we have an agenda
Okay.
from you, Alex, please?
Yeah, not a problem.
Okay, cool. Okay, so that's all the comments that I've particularly got to make at this stage. Will?
I'll focus mainly on what I think I'd be bring best to the party. So that's the Arduino side and the electronics side. So if I start an email conversation with Ben and your software guy, so I forgot it.
Yeah.
To get that going, then that's where I'm going to benefit you guys the most. I was just wondering as well, in project meetings we do an around the table, and that's where everyone just says what they're doing at the time and what problems they're having, just to bounce the ideas off the other guys. You said that you sort of meet, or is it every Wednesday you meet as a whole team?
Yeah.
And so what, you're able to just discuss the problems you're having individually?
Yeah.
Yeah.
Because it's useful, because although, say, you're a software guy and no one else might be good at software programming, but if he comes up with a problem, then even those guys can come up with a good idea. I mean, what's your major problems at the moment? What's your sort of keep you up at night, so to speak?
Time is.
Time, yeah. Yeah, absolutely.
Projects as well.
So, as Pete was saying, with the forward planning, if you're able to build up that plan, then you can see what's going to take up a lot of time, but not give you added value. So, what might take 2 weeks, but won't necessarily bring much to the party. So, for example, as Pete said before, with the 3D model, in 3 months' time, is the 3D model going to benefit you, or is it worth spending that time doing something else now, i.e. like the testing, and to work out the centre of gravity with a dummy load, and to get that testing done? Does that make sense?
Yeah.
Okay, so now is the time where you guys have to start being ruthless with not with each other. Let me get this right here. You work well as a team, but you need to be ruthless with the design, and you've got to make difficult and hard decisions. And this especially goes out to the other project engineers. Is that if you find that your part of the project is being cut out or is being put to one side, then take it on the chin. Okay, roll with it, and just try and help the project out in other ways that you can possibly. Because at the end of the day, it's the CANSAT, which is the most important aspect of the project.
Yep.
Okay. So we've done a lot of talking from this side. Okay, we'd like to hear from you guys now. Tell us a bit, as we said, problems and any other sort of questions you may have.
Like we said before about Bradley, probably assigning his role to someone else while he sorts out his time management. And that's all from me so far. Anyone else? I think also testing. Assigning time for testing and
The programming issue at the moment is that some of the components that are working on Arduino that aren't working on the T- board, and how we have to assign the different connections with either digital or analog or so.
Okay. So the question I've got for you and for Alex is, how much time are you prepared to spend on this? Okay. And then if this doesn't happen, what is your backup plan? What are you going to do? Just because Esro have given you this board to fly, okay, and you're having problems, at the end of the day, you guys have got to make a decision to fly the Esro board or fly something else, and explain what the difficulties you had with the Esro board and why you then made an alternative decision. That's perfectly acceptable in the space industry world, that when we come across problems, which is especially time critical, we may fly something else, but as long as we explain it to the customer.
Yeah, okay.
Yeah, my gut feel is if you've got something working easily on an Arduino and not very easily on this Esro board, my gut feel would be to stick with the thing that you've got working. I noticed as well you've bought some Arduino shields. Do they interface to this Esro board?
Yeah.
They plug in straight on top.
Yeah.
You say the question again, please?
So with the Arduino shields I've seen you bought, the SD card and the wireless communication, they will physically fit on top of the Arduino, correct?
Yeah, they basically designed it so it fits nicely inside.
So this board that they've given you, will that accommodate physically the Arduino shields that you've bought?
It's well, they bought the components and then they'll just locate the components around the cam where they want to put it. So just wiring and stuff.
So you wire those in rather than push fit, put them on top?
Yeah, they're going to be soldered onto the board.
Okay. Just wondering of the practicalities of just getting the Arduino and just pushing the shields on top. So the sensors, are these on wires or are they on a PCB, your pressure and temperature sensors?
Oh, they're on wires. Yeah.
Okay. And then, so you've got presumably pull-up resistors, then, really?
Yeah.
Are they built into the wiring of the sensors, or is this something that you've got to put on another board?
They're all our components are actually 5 volts.
Okay.
Or they're all
3.3 to 5.5.
Yeah. They've all been in their specification. They can be run at either.
Okay, so you just plug those into the spare pins on the Arduino.
Yeah.
Okay, cool. So you were talking about using different temperature and pressure sensors for redundancy. That's excellent. That is a major building block of what we do in the space industry. To have a backup and definitely of different kinds is really useful. So are they all performing similar to each other? Do they all produce the same sort of readings?
Yeah, they're all performing the same simple reading on the, like I said, on the Arduino board, but nothing so far on the T-. But they all seem to be giving the correct readings.
Okay. So So when you said you were avoiding calibrating them at the moment, I think that's a good idea. You don't need to do that just yet. But what were your ideas of doing that, calibrating them against each other?
We have an external sensor that's already been calibrated from a data logger. Sorry,
Okay.
that's already been calibrated, so it's by another company, and we're just going to compare our components to the temperature or the humidity or whatever that provides to us.
And all the
Brilliant.
readings come through in.
That's perfect. That's great. Okay then. I'll get to it later. I don't want to waste too much time on it, but I am really interested in the boards that you'll be using.
Uh-huh.
Yeah. I think, yes, I emailed you the data sheets of the boards. Yeah.
Okay, so going back to your question about testing, okay, so just to describe what we do at SSTL, we have, when we build a satellite, we have what's known as an SQM, which is a structural qualification model, and in parallel we have the actual flight model, okay? And the SQM allows us to do certain tests, okay, whilst we are getting on with the work and actually building the actual satellite. So the SQM is, in your case, would be the can, and inside it would have mass dummies representing the different aspects of the components that you have in your satellite, and those will be distributed around. So you'll have 30 gram mass in the center where your Arduino board is. You maybe have a 50 gram mass at the top to represent the antennas.
Yeah.
You may then have a 40 gram mass at the bottom to represent your widgets, your gadgets, etc., etc. And so having an SQM model will allow you to get on with drop tests, will allow you to get on with seeing if you're going to have a tumbling issue, will allow you to get on and just crack on with some testing, whilst the other guys are getting on with designing their particular components and areas. All right?
Yeah.
Okay, so we have a parallel kind of system. On that, then there's the actual test itself. So a lot of this project, I think, is to do with the survivability of the system when it impacts the ground. That, I think, is going to be your critical failure area of the satellite. So I believe that is what you guys need to focus on. So trying to ensure that your satellite will survive an impact of those magnitudes.
Yeah.
So basically, lots and lots of drop tests. Also, as I said, like last time, thermal tests, vacuum tests, vibration tests are all very handy as well.
One way you might be able to quantify your drop test. Are you guys familiar with shock watches? They're like green, red, and orange stickers, and they put them on the side of boxes, so that if they're dropped, there's a little tablet in there that will pop and go red if it's experienced more than 10 Gs, 20 Gs, or whatever.
Yeah.
I've seen those before.
Yeah, I've seen them on Mythbusters.
Yeah, that's it. Yeah, absolutely. They use them on Mythbusters. Yeah, so that's maybe a way to do it. You could, if you build this SQM as Pete's saying,
put these sensors all around.
Yeah, and then you drop that out your window, and then you can then say this will experience a minimum of 10 G, whatever. I mean, you've seen the show. So that's possibly a really quick way, if you can get your hands on those sensors, to justify or to put in your report the sort of G forces you will see without having to do any accelerometers or any calculations as such, or any 3D models. It's a really quick and cheap way of doing it.
Yeah.
Yeah, thanks. Yeah.
Alright, so you guys are thinking of coming to SSTL to do a bit of presentation, have a tour. We'll try and get you into the actual clean room. I've had it confirmed from my boss's boss that he's happy for you to come in later in the afternoon.
Okay.
And we'll actually try and maybe, if there's the opportunity of you guys actually getting your hands on a real satellite, and actually building parts of a real satellite.
Oh, that'd be cool.
So that should be pretty good fun. The other things that you could do testing-wise is you could do some electrical testing here at SSTL, and you could potentially, you'll have to speak to Will, and he'll have to try and organise it, but you might be able to gain access to one of the ovens, and you can potentially do some thermal testing here at SSTL. Our vibration table is in a place called Borden, which is halfway between Guildford and Portsmouth. So I don't think you'll be able to do the vibration testing at SSTL.
Okay.
That's not to say that if you don't get a broken down or get a dryer or a washing machine and stick your system on a washing machine and a full spin, that should be more than enough to do your test as well.
Yeah.
Okay, cool.
Right, they've got a lesson in 5 minutes, so
Right.
yeah, if we can round up.
Yeah.
Yeah, that's fine.
Yeah.
In your own words, what are the 3 or 4 main points that you're going to take away from this?
Time management in regards to building the satellite and testing it.
Simpler methods, so not trying to always go for the electrical route. Simple things that work well.
Okay, yeah, good.
Work on the programming part. If try and get it working in one. So if it doesn't really work with the T- board, maybe try and focus on working with the Arduino instead.
Okay, that's good.
I'll probably also come up with some backups just in case. Trying to see if we can't get the T- board to work, other ways we can fit just a general Arduino board into our satellite.
Yeah.
Okay. Anything else?
Probably the robotic arm. To
Okay.
maybe look at another way to collect soil, like the drill.
Okay. And the big one for you, Alex, is documentation.
Yeah.
Right.
Always documentation.
Okay. So basically, good luck, guys, from us here at SSTL. I really do want to stress that if you've got any questions whatsoever, feel free to email myself or Will here, and we will help you as much as we can. But if you don't send us questions, we can't help you. Okay?
Yeah, understood.
Yeah, thanks.
Thank you.
Thank you.
All right.
Cool. Well done, guys. Really impressive project so far. It looks really, really good, and it looks like you've got some really fun stuff lined up as well. Brilliant. Well done.
Thanks.
Thank you.
Thanks.
All right. Catch you later, guys.
Bye.
Okay then. See you then.
Bye.
Bye-bye.